So we will look at the method of undetermined coefficients by looking literally at a homework problem as an example. So here it is. So I'm going to port this over to the board. So here is our second order linear non-homogeneous differential equation with constant coefficients. And you see there's no x prime term, so there could have been like plus 7x prime or something, but this one just doesn't have it. And I'm choosing this one because I'm lazy and I want to write less. So let's define the left-hand side to be L x of t. So let's just view this as this kind of linear system where, and we should say what L is now. L x of t means the left-hand side here. So maybe a better way, more informative way to put it is just to say what L is. L is take two time derivatives, and plus 6. So I'm just writing plus 6 because the idea is that the left-hand side here is L applied to x. So when this gets applied to x, the 6 represents actually the operation of multiplying by 6. That's why it's just plus 6 there. So it's kind of like 6 times the identity operator or something like that. But we just write 6. So remember from the last video, the technique was get the general solution to the homogeneous version. We know how to do that, and we'll do it in a moment. And get just one solution to the non-homogeneous. So if we want the general solution to this thing here, then to apply the strategy suggested here, we just need one solution to this. So we want one solution, just any solution to this thing, by any means necessary. So if we have to lie, cheat, and steal to get our one solution to this thing, then maybe that's what we would do. Okay, but I don't really mean lie, cheat, and steal. I mean kind of crappily guess things. But it's actually not that crappy if you remember that L here is a linear operator. So I'll show you how that helps you. Okay, so to get our one solution, we basically want to figure out a function x so that when we apply L to this x, that specifically te to the 3t comes out. Right, that's what we want. So what might you try to get that to happen? So one thing you can try is actually putting in te to the 3t. I mean, why not? Like, if you want te to the 3t to come out, at least maybe I mean, definitely it's not going to be that just putting in te to the 3t is going to work, that it gives you te to the 3t, but it'll at least give you something similar, and that'll give us some information. So let me start by just putting in te to the 3t and see what comes out. So applying L to this, so applying this linear operator to this, first I have to take two derivatives. So, okay, this will take some scratch work. So one derivative applied to te to the 3t gives me, by the product rule, e to the 3t plus 3t e to the 3t. And now if I apply two derivatives, like this, then I get 3e to the 3t plus, and then I have to use the product rule on this thing. So I get 3e to the 3t plus 9, another 3 comes down, te to the 3t. Okay, so that's the first term of this thing. is, let me simplify this a little bit, 6e to the 3t plus 9t e to the 3t. So the first term of this thing is, okay, so do you see where this is coming from? I'm applying L to this. That basically means determine what is the left-hand side here when I plug in x equals this. Or in other words, apply this to this. So let me just write it step by step. So I'm taking this and applying it to this. You see? That is what I'm doing. And I'm working out the first term. So that's what I was doing here, is I was working out what happens when this applies to this. Apparently I get 6 e to the 3t plus 9 t e to the 3t. And then there's another term which is 6 times this. So 6t e to the 3t. Okay, so what I get when I do this, just simplifying, it looks like I get 6e to the 3t plus 15 te to the 3t. So that's interesting. That's not exactly what I wanted, but it's pretty useful information. So let me just log that away and remember that. Okay, so you see how it's not what I wanted? I wanted to plug in something into L and then get out te to the 3t, right? But what I've done is I've plugged in something and I've gotten out this instead. It's not te to the 3t, but it involves te to the 3t. It's a linear combination of two functions, one of which is te to the 3t, right? It's a linear combination of e to the 3t and te to the 3t. So it didn't give me what I want out, but it gave me a linear combination of two things, one of which is the one that I want out. So this was a pretty good guess to start with, actually. You know what would have been a bad guess is if I plugged in te to the 7t or something like that. If I just didn't put 3 here, if I put some random number, that would be a bad guess, because then not only would I not get what I want out, not only would I not get te to the 3t out, I wouldn't even get a linear combination that involves that. So this is not so bad of a guess. At least the thing that I want to come out appears as one of the sort of vectors in this linear combination. Okay, so how can I go from this to finding something that I can plug in to get only te to the 3t? Well, if I could find something to plug in that gives me out e to the 3t, or a linear combination of e to the 3t with some other things maybe, then we might be able to go places with that. And if you're not seeing why, if your sort of linear algebra intuition is not screaming at you that that's the right thing to do, then that's fine. We don't necessarily expect you to have that intuition at this point, but watch where it goes. So let's see if we can get e to the 3t to come out. And remember, L is this. So how can I get e to the 3t or something similar to come out? How about plugging in e to the 3t? So let's try plugging in e to the 3t. And what do we get? So we have basically this applied to e to the 3t. So that gives me two terms. With the double derivative applied to this, 2 3's come down, so I get 9e to the 3t plus, and then 6e to the 3t. Interesting, so I got 15 e to the 3t. All right, so it looks like I found something that when I put it in gives me this linear combination, and something that when I put it in gives me this. So let me underline similar vectors, or where you have the same vector. So think of this vector as sort of the green vector, the green direction, and here we've got the blue vector, te to the 3t, showing up there. I want just a TE to the 3t to come out. Remember, L is linear. So if I take a linear combination of vectors and then I insert that linear combination in as an input to L, then what comes out will be a linear combination of the outputs with the same coefficients. So that's what I'm going to use to my advantage. So can we find a linear combination of this and this so that what comes out is just the blue vector, pure blue? That would be a solution to this thing. Just one solution. It would be one solution. But we also have this deal that I haven't shown you explicitly how to work out, but I will, where if we just have one solution to this, then we are golden. Okay. So remembering these facts, that when you input this, you get this. When you input this, you get this. The question is, can we, how about I put it this way, is there some linear combination, let's call it A TE to the 3t, with some number A here, plus B E to the 3t, so a linear combination of these two inputs, this one and this one, so that L, when you apply it to this linear combination, you actually get pure blue vector, TE to the 3t. Is it possible to choose these coefficients so that this happens? Well, let's see. We can actually work out what this is, and now it's easy with the information that we've collected so far. So let's work out what this is. This is, since L is linear, it's A L TE to the 3t. Let me stick to square brackets. Plus B L E to the 3t, both of which are things we computed, right? This one and this one were computed up here. So this one, L of TE to the 3t, that's what we computed up here. Half the computation disappeared, but this is what it ended up with. So this is A times 6 e to the 3t plus 15 TE to the 3t. Plus B times L of this, we computed that, we got this, 15 e to the 3t. Now the colored parts that I'm showing you, we're thinking of these as vectors, and in fact they are linearly independent vectors. We've actually discussed the linear independence of these two kinds of functions. And look what we're trying to get to work. So our question is, is there some choice of coefficients, A and B, so that L of this equals this blue? So in other words, is there a way to choose A and B so that this blue vector here equals this junk down here? This junk down here is a linear combination of green and blue, right? So this is 6A plus 15B of green, that much of green, and then how much of blue? 15A. Like that. So we have this coefficient green plus that coefficient blue, and we'd like to choose A and B so that this gives me TE to the 3t. Looks like a linear algebra problem, right? So if the blue and the green are really linearly independent vectors, then how can how can I choose these coefficients here so that this works out? There's only one way. This has to be 0. So let me write what we want. Let me try to make this a little bit more clear. We want this equals this. This is what we want. We want to choose A and B so that this happens. And what I'm saying is that this happens when this is 0. So we want this to be 0, and we want this to be 1. That's the only way to get a this linear combination to end up just giving me 1 times this one. Okay, so that's two equations with two unknowns, right? So we can solve this system of equations. So we get 6a plus 15b equals 0, and 15a equals 1. Okay, so you're going to get a lot of equations like this, and some of them are not going to be so nice to you and give you something like 15a equals 1, where you can just solve so easily. You'll have to do a bunch of algebra, which is not fun. So, well, maybe it's fun for you, but either way, if it's not fun for you, I very strongly recommend using a computer algebra system, like Mathematica is the one that I've been showing you guys, but if you're familiar with something else, you use that. But here, this one's easy, so I can just do it here. A is 1/15th, and that means this says 15b is minus 6a is minus 6/15ths. So then b is minus 6 over 15 squared. So I have found what coefficients a and b make it so that L of this linear combination is this te to the 3t. So I've actually achieved this step of what I was describing earlier, where I just get one solution to the non-homogeneous differential equation. So therefore, let's call it x sub p for a particular solution. 1/15th of, let's see, what was big A sitting in front of? te to the 3t. And negative 6/15ths squared, e to the 3t, is a particular solution. It's just one solution to our original differential equation, which was Lx equals te to the 3t. Let me write out the whole thing now. X prime prime plus 6x equals te to the 3t. Okay, now there are a lot of places where I could have made algebra mistakes, so at this point I'll stop and check that what I'm saying is correct. This really is a solution. So in the middle of typing this, I realized I included the negative sign twice. And there. So here I'm defining the function xp. There it is. Then I want to verify that it solves this differential equation. So how about I just can work out, or have it work out what is x particular prime prime of t plus 6 x of t. And then it'll be something, oh sorry, x particular. And then it's something which needs to be simplified. So let's simplify that. And my hope is that it ends up being the desired right-hand side here. Oh, wonderful, te to the 3t. So now I know that I really have found one solution to this. So earlier I told you this was called the method of undetermined coefficients. Do you see why? Sorry. The way we did this was we came up with a guess, and our guess is a linear combination with some coefficients. You could say that these coefficients are undetermined. And then we determined the coefficients a and b by just demanding that we have a solution to the non-homogeneous equation. So these are the undetermined coefficients. This is the method of undetermined coefficients, which is a fancy way of describing this kind of educated guessing. So it is guessing, but it's not totally random, right? We were using some reasoning about what kinds of things we think when going in would give us the ingredients that we want to come out. And you know, if you put in enough of the things that give you the ingredients that you want out, then, like here we just had to put in these two, then maybe you can find a linear combination of those ingredients, some concoction that gives you exactly what you want out. And while you don't know exactly what concoction, what linear combination is going to work, you can leave the coefficients undetermined and determine them by imposing the differential equation. This is what we did. Great. So so far I have only shown you a portion of the plan, and I feel like this is what it all looks like to you probably, where I'm saying, you know, find a particular solution, x sub p, to the non-homogeneous differential equation. That is what we did here. We found that this is one solution. Particular just means a solution, a specific one. Here's a solution. It's not general, right? We cannot use it to satisfy any old initial conditions. This satisfies one particular set of initial conditions. So this is not general, it's particular. So we've done this. Okay, great. And then I'm telling you, find the general solution to this. We know how to do that. Let's actually do it in a moment. And then what happens? How do we profit? What are we supposed to do with this information? Once we do this, you add the solutions, and profit means you get the general solution. To the full original non-homogeneous differential equation. So we have done this so far. Let's do this one. This one is pretty easy in the sense that we have already learned how to do it. Okay, so, sorry, where was I? This was our original problem here. So let's go look at the homogeneous version of this. Here's the original differential equation, and here's the homogeneous version. So let's focus on the homogeneous version, where I've just put 0 on the right-hand side. And we know how to get the general solution. What we need is the general solution. Guess x equals e to the lambda t. Then you plug it in and blah, 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 and you get lambda squared plus 6 equals 0. So then lambda equals, if you solve this, plus or minus square root of 6i, right? This is like lambda squared equals negative 6, so you get this. And you're in the complex roots case, right? So that's our what we called case 3. So here's our complex solution, is x of t equals, to the homogeneous differential equation. This would not be a solution to the non-homogeneous. So complex solution to the homogeneous, x of t equals plus or minus, we just pick one, so I'm going to pick plus, is that, right? Let me write it in this order. Is that, which in terms of real and imaginary parts, here's the real part, and here's the imaginary part. Sine square root 6 times t is the imaginary part. So then the real and imaginary parts of our complex solution provide us with two linearly independent real solutions, these are linearly independent just because we know cosine and sine are linearly independent to the original, not to the original, but to the homogeneous version of the differential equation. So let's define x1 of t to be the real part, and define x2 of t to be the imaginary part. Both real functions. Then if I take c1 x1 of t plus c2 x2 of t, an arbitrary linear combination with coefficients c1 and c2 of these two linearly independent solutions to the homogeneous, then that is a good general solution to the homogeneous. So this is our x sub g, a general solution to the homogeneous, not the non-homogeneous. Great, so now we have done this. So let me summarize what we did it with specifically. So this one we got let me actually use colors. We got x sub general t equals c1 times cosine square root 6t plus c2 times sine square root 6t. And up here for this one, we got our particular solution. So remember, this is not a solution to the original differential equation. It's a solution to the homogeneous version. Here, this is a solution to the original, but it's not general. It's just one solution to the original. And let me go back and see what we got. This one, 1/15. Okay, let me just copy this over off screen. Okay, there it is copied over. And then add them. So here's the sum. X of t equals this one, this one, let's shrink everything down. And stick in a plus sign. There. And that's it. We now have gotten a general solution to this thing. Here it is. You see the C1 and C2. These are sort of free parameters that if you had any particular initial conditions, then those would tell you how you would need to choose C1 and C2. So we have now gotten the general solution. Okay. So on your homework, this whole thing is kind of broken up step by step, where I have broken it up step by step so that it sort of guides you through choosing individual things. So this suggests to you what guess to make. You saw that making the guess was kind of really required some thinking. So sometimes I will suggest to you the guess, but sometimes you have to figure out the guess, and we'll discuss that in a moment. But I just wanted to comment, since I don't use this language very often, the fundamental solutions to the homogeneous version of the differential equation. So what that refers to is over here, it refers to these two. These are the two fundamental solutions. The two linearly independent solutions whose linear combinations you later take to get a solution to the homogeneous. So these are called fundamental solutions. So what this is asking for is, it's saying enter either one of them. So let me just enter cosine square root 6t. That should be counted as correct. Yeah, so if I entered sine, then that would also be counted as correct. I'm showing you this because this question has historically confused people for some reason, since I said enter either one of them. Okay, and then over here you're just determining the undetermined coefficients and entering only those. So for us, those would be the these 1/15th and -6/15 squared that we found. And then you're finding your general solution, and then you're satisfying some initial conditions. So this is the one part that we did not do here in the lecture. This is where you just impose these two equations, and it's going to be a whole bunch of algebra, but you can do it by hand or you can use Mathematica or whatever you want to basically impose those two equations and figure out the two unknowns, C1 and C2. Notice that it would not be good enough to impose those two equations. You should not impose the initial conditions on just the blue part here, on just the solution to the homogeneous. You need to get all the way down to here and then impose the initial conditions at this level, because this red stuff is going to affect it, actually.